I will talk about idealized simulation studies about zonal convective self-aggregation. Yeah, this is collaboration work with Cathy Henniger. Yeah, first of all, ITCZ is a central component of tropical climate, but its internal structures, including the zonal variability, is not fully understood. To first order, the high sea surface temperature provide favorable conditions for deep convection. However, the recent studies suggest that convection can aggregate in the zonal direction even when the SST is zonally uniform. So this suggests that rain belt is controlled not only by local SST, but also the self-aggregation of deep convection itself. So here we ask under what condition this self-aggregation, zonal convective self-aggregation occurs and what physical mechanisms support it. So we employ a non-rotating RC framework using a cloud resolving model. It is called SCALE. This is Japanese non-hydrostatic model, but we impose a meridionally varying SST distribution. Yeah, here is the computational domain schematics. Yeah, this is a doubly periodic domain, and the domain size in x-axis is zonal direction is 6,000 kilometers, and 3,000 kilometers in the meridional direction, and grid spacing is 4 kilometers. And importantly, we vary the two control parameters, SST max and SST amplitude. In total, we conduct 12 simulations. Yes, so let's move on to the result. First, we compare the horizontal distributions of moisture in two contrasting cases. In the left panel, the left case is low SST max and low SST amplitude case. And the right panel shows a case with high SST max and high SST amplitude. In the left panels, the moisture fields shows almost uniform zonal distribution. In contrast, in the right cases, there is a clear zonal contrast of moisture, which means that in the right cases, zonal convective self-aggregation occurs. To quantify this difference, we introduced the anisotropy index, which measures the relative importance between the zonal variance of moisture field and the meridional variance of moisture, formulated like this. For example, the zonally uniform distribution exhibits a negative value of this index, and the zonally aggregated state exhibits the near zero values of this index. So the left panel shows the time evolutions of this index for all cases. So the all cases first move towards a negative value, but later they separate into two groups. Yeah, the one group stays negative, but the other groups move back towards near zero values. The right panel shows temporary averaged index during the last 30 days in the parameter space of SST max and SST amplitude. Using a threshold value of -1/3, we find that zonal convective self-aggregations occurs preferentially when both SST max and SST amplitude are high. So in the following part, we will examine the mechanism of zonal convective self-aggregation, and starting from one example of zonally aggregated case. And the left panel shows zonally averaged precipitable water and zonally averaged meridional surface wind, and the axis is y and time. Yeah, first of all, the system is characterized by the meridional convergence towards the warm domain center, and it is associated with the moisture contrast. At the same time, we can find that this meridional structures shows temporal oscillation, specifically the strong convergence and weak convergence, strong convergence, weak convergence. And the right panel shows the meridionally averaged precipitable water and the meridionally averaged zonal surface wind. And the axis is x and time. And we can note that this zonal contrast of moisture and circulation develops after one of the weak meridional weak meridional surface convergence. So it suggests that the weak meridional surface convergence provide favorable conditions for the following development of zonal aggregations. And next, we ask if this weak meridional convergence is common for other zonal aggregation cases. So the left panel shows the temporal minimum of zonal meridional convergence. Zonally averaged meridional surface convergence. Here, the meridional convergence is quantified by the meridional maximum and the difference between meridional maximum and minimum of the zonally averaged meridional surface spin. So we can see that all zonal aggregation cases exhibit a weak experience of weak meridional convergence. Right? So it suggests that weak meridional convergence is a common features for the zonal aggregation cases. So we ask what caused this weak meridional convergence. And we interpret this using a simple momentum balance in the boundary layer, and in which the surface frictional damping and the pressure gradient force balances. And if we assume that surface friction scales with surface meridional wind as well as the surface convergence, weak meridional surface convergence can be attributed to weak pressure gradient or shallow boundary layer. Here we show the pressure gradient force and the boundary layer depth. And importantly, first of all, the weak convergence is not associated with weak pressure gradient force. Instead, it is associated with shallow boundary layer. It suggests that this weak meridional convergence is caused by strong surface frictional damping caused by the shallow boundary layer. So the next question is what caused shallow boundary layer? And here we interpret this using a scaling relationship in which the boundary layer depth increases with shallow surface buoyancy flux and decreases with lower tropospheric stability and tropospheric subsidence. Here we show the three controlling factors, and in short, and only the lower tropospheric stability could explain the shallow boundary layer depth, especially in the high SST max and high SST amplitude. Here, in high SST max and high SST amplitude, we have a higher lower tropospheric stability, which causes shallow boundary layer, and it causes stronger momentum damping. So to summarize, zonal convective self-aggregations occurs when both SST max and SST amplitude are high, and the zonal convective self-aggregation cases experience a weak meridional convergence. And the weak meridional convergence is due to strong frictional damping, a shallow boundary layer, and the high stability. And also this high stability in higher SST max and higher SST amplitude can be interpreted physically. For example, for a fixed SST amplitude, increasing the SST max forms a free troposphere through most adiabatic control. And also for a fixed SST max, increasing the SST amplitude cools the boundary layer through local SST control. So these two parameters both contribute to the higher stability. For these reasons, higher SST max and higher SST amplitude provide favorable conditions for zonal aggregation. That's all. Thank you.
Thanks, Tomoro. Questions? I think we have good amount of time for questions.
Thanks. This is nice. One of your plots showed there was this oscillation in the meridional convergence.
Oh, you had a question.
Yeah. This is important feature. Yeah. For example,
Yeah. Do you know? So this must be being generated internally, right? There is no diurnal cycle. There is no.
No, this is internal dynamics.
Have you examined what causes this?
Yeah, that's a good point. Actually, I examine some variables and I check some consistency, but I cannot clear answer about it. Yeah, but it's consistent. For example, if we have stronger convergence, it has a higher moisture contrast, but then it produces, how to say, stronger convection, but it damps the circulation, and then the moisture contrast weakens. So I have some consistency, but exact reason is not clear. And I'm very curious about what happens for this oscillation. But yeah, that's next.
Yeah, and maybe a quick follow-up. Will you see the same zonal aggregation if you have a rotating RC? How does F change when you have rotation in your...
A rotation?
Yeah.
I don't know actually. So maybe rotation. I think the rotation is very important for the next step. So maybe actually it should change the momentum balance, and also probably it changes circulations horizontal scale through the deformation radius or something like that. Maybe so that's the next step.
Yeah. Thank you.
Well, if there are no more questions, let's thank Tomoro for a nice talk.